Hello, I'm Yulei from Tsinghua University. I'm very glad to share our paper about detecting OS bugs. OS is a cornerstone for modern computer systems. It manages hardware devices and provides fundamental services for user-level applications. And today, there are various kinds of operating systems. The code of an OS is very complex and contains substantial variables. A modern OS typically consists of numerous modules, and each module interacts with others through function pointers. Calling relationships of a function can be complicated due to indirect function calls through these pointers. Besides, OS uses pointers and data structures heavily. The figure shows a piece of code of the module S5P-MFC in Linux 5.6. The pointer to S5P-MFC probe is stored in the field .probe and acts as a module interface. Its function can be implicitly called through multiple module interfaces like this, making calling relationships in an OS quite complicated. Besides, to improve performance, data is usually passed using pointers and data structures such as line 1000-280 in this example, causing alias relationships in an OS to be very complicated. However, OS code is error-prone. First, an OS has rich functionalities and various kinds of possible errors. Then, developers may be incautious about code logic and introduce bugs by mistake. Besides, OS code is often not well documented, and thus APIs can be misused. Bugs in an OS are dangerous, and even a simple OS bug can cause system crash, malicious attack, data corruption, and so on. Therefore, detecting OS bugs is important. Static analysis is an effective approach to detect bugs. First, due to high code coverage, static analysis can detect bugs in regularly executed code paths. Then, OS needs not to be executed when performing static analysis. Besides, static tools are easy to deploy. However, there are limitations of static analysis. For example, alias analysis is not quite precise, and detecting multiple types of bugs is inefficient. Besides, the false positive rate is high when performing bug detection statically. This figure shows a real non-pointer dereference in Zephyr. In the function friend set, the pointer CFG is first assigned with the field user data of model at line 2709, and then it is compared to none in an if check at line 2720. This indicates that CFG and user data of model can be none. If so, the function sendFriend status is called with model at line 2748. In this function, the pointer CFG is assigned with the field user data of model at line 2684. In this case, CFG can be none, and a non-pointer dereference may occur when the field FRND of CFG is accessed at line 2687. This bug involves multiple alias relationships of data structure fields across multiple functions and is hard to find. According to the above analysis, there are three main challenges in detecting OS bugs. First, because of the multi-module nature of OSs, many functions are called through pointers and have no explicit caller functions, and their pointer parameters can have incomplete pointer size. Therefore, computing alias relationships of two pointers by identifying whether their pointer size have intersections can be imprecise. Moreover, alias relationships can be quite different in different code paths, and only performing flow-sensitive analysis may cause imprecise alias relationships for its code path. Second, type-state analysis is effective to detect multiple types of bugs in software, but OS has a large code base with substantial variables, and thus tracking type state of each variable is quite expensive. Third, there are lots of code paths in operating systems, and validating all possible code paths can be very costly. To address the above three challenges, we propose three key techniques. A path-based alias analysis will effectively identify alias relationships based on counter flow paths and access paths. An alias-aware typestate tracking method to detect multiple types of bugs, and an alias-aware path validation method to drop false positives efficiently. We use alias graph to represent alias relationships in our paper. In an alias graph, each node represents an alias site that points to one abstract object. Each labeled edge represents how an abstract object is accessed, and the label of each edge can be a data structure field or a dereference operator. A variable residing in a node followed by a sequence of edge labels from an access path, and the access path ending with the same node on an alias graph forms an alias site. The figure shows an alias graph. Take node 4 as an example. There are 5 access paths ending with it as shown in figure B. The 5 access paths form the alias site of node 4, and the 5 variables represented by them can be inferred to be aliases. Path-based alias analysis is performed by building and updating alias graphs according to program instructions that can handle alias relationships in LLVM. For the move instruction, we move variable v1 from node n1 to node n2. After this operation, variables v1 and v2 are represented by the same node n2 with index that the two variables become aliases. The move instruction is not an LLVM instruction, and we introduce it to represent operations such as parameter passings and returns of functions. For the store instruction, we add a directed edge labeled with a dereference operator from node n2 to node n1. If there is an edge labeled with a dereference operator from node n2, we drop it. After this operation, variables v1 and dereference v2 are represented by the same node n1. This index the two variables become aliases. For the load operation, we move variable v1 to a desk node of the directed edge labeled with the dereference operator from node n2. After this operation, variables v1 and dereference v2 are represented by the same node nx. For the LLVM get element PTR instruction GEP, it is similar to the load instruction, except that the is labeled with a data structure field F instead of a dereference operator. The figure shows an example of our path-based alias analysis. We exploit func:\v to represent the variable v in the function func. Each node in the alias graph represents an alias site. Through a GEP operation and a load operation, our analysis gets the alias graph at line 3. For the if statement at line 4, our analysis copies the alias graph into 2 branches. Take the true branch as an example. When calling bar, our analysis performs the move operation between the formal parameter and the actual parameter, and gets the alias graph at line 5. It indicates that the variable p in functions foo and bar are aliases. And then through a GEP operation and 2 load operations, our alias analysis finally gets the alias graph at line 12. Static type state analysis defines some type states to describe possible states that its variable can reach, and then tracks type state transitions according to related operations to detect bugs. A type state property can be specified as a finite state method, namely FSM. The FSM can be described as a quintable, in which sigma is the set of instructions in a program that change the state. S in blackboard board is the set of all possible states. S0 is the initial state. Data is a set of state transition functions that map the present state and an instruction into a new state. S-tab is a final state, which means a possible bug is detected. However, alias variables can share the same state in an FSM, and thus our analysis maps alias variables into the same state in an FSM, which can reduce states and state transitions. We have implemented 3 FSMs to detect non-pointed dereference and initialize variable accesses and memory leaks. Take a non-pointer dereference as an example. This FSM contains 2 states apart from the initial state and the final state as NPD. As none means an alias site is not none. As n means an alias site is none. The FSM also contains 4 instructions related to non-pointer dereference detection. Assign none to a pointer. Execute a branch of an if statement where the pointer is none. Execute a branch of an if statement where the pointer is not none. dereference a pointer. We use state transition diagram shown in the figure to illustrate the state transition function data. The FSM shows that if a pointer is judged to be none at an if statement or assigned with the none value, and then be dereferenced, a non-pointer dereference may occur. The figure shows a piece of source code we have analyzed when introducing our path-based alias analysis. There is a possible non-pointer dereference in the source code. We use this example to illustrate how to reduce states and state transitions with alias relationships. Without alias relationships to detect the non-pointer dereference, typestate analysis should maintain states for variable t in function 4 and 8 in function bar separately, and transfer the state of t in function bar to none when analyzing it at line 11. There are 5 states and 3 state transitions as shown in figure A. However, alias variables share the same state, thus their states can be merged and synchronization like line 11 in this example can be dropped. As shown in figure B, our analysis only maintains a state for the alias side that contains variable t in 4 and bar. Finally, there are 2 less states and 1 less state transition than traditional typestate analysis when performing Alias-Aware Typestate analysis. When a possible bug is detected, our analysis uses a SMT server Z3 to verify the code path. Alias variables should satisfy the same constraints in a given code path, and thus our analysis maps alias variables into the same symbol in an SMT server. We use R to represent such map. To get path constraints, our analysis translates its instruction in the tested code path to an SMT constraint. For example, our analysis translates the statement assign B plus C to A to the SMT constraint RA is equal to RB plus RC. As for the statement if E, our analysis translates it to RE is equal to 1 for the true counterflow branch, and to RE is equal to 0 for the false counterflow branch. At last, our analysis uses 3 to solve all the constraints. If the constraint cannot be satisfied, the possible bug is identified as a false positive and is dropped. The figure shows an example to simplify SMT constraints with alias relationships. We use R' to map a variable into an SMT symbol without considering alias relationships. To validate the code path of a possible non-pointing dereference, namely lines 2, 3, 4, 6, and 7, we need to translate the instructions in the code path to SMT constraint. Without considering alias relationships, for each assignment like assign P2 to P1, we need to add an explicit constraint R' P1 is equal to R' P2. Moreover, if P1 and P2 are data structure pointers of the same type, each of their field F should be equal. Thus, we need to add implicit constraints as shown in the top of figure B, in which the error means implication. However, by considering alias relationships, if 2 variables P1 and P2 become aliases, our analysis maps them into the same symbol in an SMT solver. And thus, P1 is equal to P2 is naturally satisfied. In this example, the explicit constraint at line 4 in figure B can be dropped. Moreover, if P1 and P2 become aliases, their fields such as F are also aliases and will be mapped into the same symbol, and thus, all the implicit constraint can be also dropped. Comparing figure B and figure C, we can find that using alias relationships can effectively simplify SMT constraints. In this example, 1 constraints are dropped. Based on the 3 key techniques, we propose a novel approach named PATA to statically detect multiple types of bugs in OSs. We have implemented PATA using LLVM, and the figure shows its framework. We evaluate PATA on the Linux kernel and 3 open source IoT OSs, including Zephyr, IoT, and TinyOS 10. We have implemented 3 FSMs to detect non-pointer dereference and initialized variable accesses and memory leaks, because these 3 types of bugs are common and dangerous in OSs. The table shows our evaluation results. As the table shows, by using alias relationships, our analysis can reduce about half of the type states and 87% of the assembly constraints, which illustrates that our alias-aware typestate tracking method and alias-aware path validation method are effective. PATA total reports 797 bugs, and we identify that 574 of them are real, including 463 non-pointer dereferences, 19 uninitialized variable accesses, and 21 memory leaks, and 206 of them have been confirmed by OS developers. We also experimentally compare PATA to 7 state-of-the-art static tools, and this table shows the comparison results. 328 of bugs found by PATA are missed by the 7 tools, but only 27 of bugs found by the 7 tools are missed by PATA. Indeed, the source files containing the 27 missed bugs are not compiled with the compilation configurations used in our evaluation, and thus these source files are not checked by PATA. Besides, PATA has a much lower false positive rate than 7 static tools. PATA still has some limitations. For example, it does not handle array elements with non-constant array indexes and functions with a variable number of parameters. Besides, PATA neglects the concurrence of memory accesses. Not handling this phenomenon will introduce false positives. PATA also does not handle function pointer calls and undo its loop and recursive call just once, which can introduce false negatives. At last, we make a conclusion of our paper. OS has a complex code base with many hard-to-find bugs. To effectively detect OS bugs, we propose a novel approach named PATA. It has 3 key techniques. A path-based alias analysis to effectively identify alias relationships based on control flow paths and access paths. An alias-aware typestate tracking method to detect multiple types of bugs. An alias-aware path validation method to drop false positives efficiently. We have evaluated PATA in the Linux kernel and 3 IoT OSs. It totally found 574 real bugs and outperformed 7 state-of-the-art approaches. That's all. Thanks for listening. If you have any questions, please contact us.